When you look at a massive steel bridge or a towering skyscraper, it's easy to just see the sheer strength.
Absolutely. They're impressive.
But then you remember, these things are absolutely peppered with holes. Holes for bolts, for connections, for, well, everything that holds the pieces together.
Uh-huh.
How do engineers deal with that? How do they make sure the spots where you've essentially punched a hole in the steel, the areas that are clearly weaker, don't fail unexpectedly?
It's one of the fundamental challenges in structural design, really. Those holes reduce the effective area carrying the load, and they also concentrate stress right around the edges.
Yeah.
It's a critical detail.
And it's exactly what we're diving into today. Welcome to a deep dive into the fascinating world of structural steel design, specifically focusing on how engineers think about failure in those critical areas with holes.
Especially when the steel is under tension being pulled apart.
Right. Our source for this deep dive is a recent experimental study published in Fracture and Structural Integrity.
Ah, yes. This paper by Leonetti van Schuppen, Jehanian, Mobder, and Snyder, they really zeroed in on something called net cross-sectional failure, basically. Failure happening in that reduced area around the holes.
And they looked at plates that might even have small damage, like tiny cracks.
Exactly. That was a key part of it.
So our mission today is to unpack this research. We want to understand what it tells us, how it stacks up against the existing rules engineers use, like those in the Eurocode standard, and what new insights it brings about with factors you might not immediately think of, like these small cracks, different types of steel, and even the effect of low temperature.
And we'll also touch on how a sophisticated tool called the Failure Assessment Diagram, or FAD, plays a role in this kind of analysis.
Okay. And why should you, our listener, care?
Well, because understanding how these crucial details are analyzed helps you appreciate the incredible safety margins built into the infrastructure all around us.
You mean the bridges you drive over, the buildings you enter every day?
Precisely. It's about peeling back the layers of engineering to see the rigorous science and testing that keeps things standing safely.
Absolutely. So let's start with the playbook engineers use. In Europe, the go-to standards for designing steel structures are the Eurocodes, right? Specifically Eurocode 3.
That's the main one, EN 1993. And if they're using stronger steel, say up to S700 grade, they're also referred to specific parts like EN 1993-112.
And these codes provide the essential rules to ensure structures don't fail in various ways.
Yes, and as you mentioned, a really important scenario is steel elements loaded in tension, especially when they have holes for bolts or other connections.
Right, because those holes are like built-in weak spots. Less material means less capacity, and the stress tends to pile up right at the edges of the hole.
Exactly. The code recognizes this potential issue. Failure can happen in that net area around the hole before the entire piece of steel even starts to yield or stretch uniformly.
And that kind of premature failure at a hole, well, it isn't ideal, is it? You lose that nice ductile behavior, the ability of the steel to deform and maybe redistribute load.
That's the concern. So
Right.
the core requirement in Eurocode 3 is pretty straightforward. The force you apply to the element, what they call NED, the design load,
Yeah.
it must be less than or equal to its calculated tension resistance, which they call NTRD.
Okay, NED, less than or equal to NTRID, it's simple enough. But how does the code say you calculate that resistance, that NTROD?
It's actually a conservative approach.
Sure.
The code tells you to calculate two different resistance values, and your design resistance, NTRD, is the lower of the two.
Two values, okay, what are they?
One is the resistance based on the entire or gross cross-section of the steel yielding, basically, the whole piece stretching. That's NPLRDD.
NPLRD, got it, gross section yielding.
The other is the resistance based on that reduced net area around the holes reaching its ultimate strength. Think of it as a point where the material in that smaller area actually breaks. That one's called new grinder.
Ah, okay. So you check the strength if the whole thing stretches, and you check the strength if it just breaks locally at the holes, and you have to be safe against whichever one happens first, the weaker one.
Precisely.
And we're focusing on that second one, new lard, the net area ultimate resistance. What's the formula for that in the Eurocode?
Well, the basic formula involves taking the net cross-sectional area, a net.
That's the area minus the whole area.
Right. You multiply that by the ultimate tensile strength of the steel, Fu. Then you divide by a partial safety factor.
Safety factor, of course.
Yeah, typically called DIM-M2 or GAM12 for high-strength steel, though the code often recommends using the same value for both in practice.
Okay, so net times Fu divided by a safety factor. Seems straightforward. But this is where the paper we're looking at highlights something specific, isn't it? There's an extra factor tucked in there.
Correct. There's a factor of 0.9 applied in the Eurocode formula.
0.9.
Yeah. The actual formula for new lard is a net foo 0.9 game 2, or game 12. That 0.9 is a direct reduction applied right to the calculated resistance.
A 10% reduction, just like that. Why is that 0.9 there? Where did it come from? Is it just arbitrary?
Oh, no, not arbitrary. According to the Eurocode commentary and background documents, this factor is based on, well, decades of previous experimental tests and fracture mechanics safety assessments.
Okay.
It was specifically introduced to provide an extra margin. It's intended to account for things like the potential presence of small pre-existing cracks around bolt holes.
Cracks you might not even see.
Exactly. Tiny defects that aren't obvious during fabrication or inspection. So it builds in a bit of robustness against that uncertainty.
Ah, so it's a safety net specifically for those hidden potential weak points like tiny cracks. That's interesting. And this factor, this 0.9, it's actually a point of discussion internationally, right?
It is, yeah. Other major standards like the AISE 360 specification commonly used in the United States, they do not include this explicit 0.9 factor in their net section resistance formula.
Really? So they calculate it differently.
The basic concept is similar, but they handle the safety margins differently without that specific 0.9 multiplier. And there's been research over the years, studies by people like Rombouts and Snyder, questioning whether this 0.9 factor in the Eurocode is perhaps overly conservative. Some research suggests it might potentially be omitted or maybe adjusted, perhaps combined within the main partial safety factor.
Interesting. So Eurocode adds this extra safety margin, maybe for potential cracks, while others don't. And there's a bit of a debate about whether it's strictly necessary or maybe too cautious.
That's a fair summary. It also ties into the broader concept of capacity design.
Capacity design. Trying to make sure failure happens in a predictable way.
Exactly. A key principle in earthquake engineering, but relevant here too, is wanting the steel to fail in a ductile manner. You want to stretch and deform significantly before it breaks, rather than having a sudden brittle fracture.
To do some warning.
Right. Ideally, you want the whole gross section to yield, NPL, air out ear, before the net section fractures, new ARD. Applying that 0.9 factor makes the calculated new ARD value lower, which makes it more likely that NPR governs the design, pushing the failure mode towards that more desirable ductile yielding of the whole member.
Got it. So the 0.9 factor is a deliberate conservatism, partly for potential cracks, and it also helps steer designs towards ductile failure.
Okay. Now, this new study we're looking at, it jumps right into that conversation, doesn't it? Builds on previous work.
Exactly. Previous studies, like one by Bearson and colleagues, had looked at the effect of cracks, but maybe focused on standard S275 steel. This new paper takes it a few steps further.
How so? What did they test that was different?
Well, they decided to look at the effect of relatively small cracks, similar to previous work in some ways, but they also introduced another variable, low temperature.
Ah, the cold.
Yes. The effect of cold hadn't really been studied much in this specific context before, especially not on high-strength steel like S700MC. And that was another focus, high-strength steel.
Yes, S700MC was the other key addition, testing it alongside the more common S275JR grade.
Okay, so their main questions were, how do different hole configurations and these small fatigue cracks affect the strength of both standard S275JR steel and this high-strength S700MC? And crucially, what's the effect of low temperature on that S700MC in this scenario? And finally, can that failure assessment diagram tool actually predict what happens?
Those are the core objectives, and to answer them, they ran a pretty comprehensive set of experiments, 51 tests in total.
51, wow.
Yeah, using both S275JR steel and S700MC. And they very carefully measured the actual material properties of their specific steel batches first, which is vital for comparing results to theory.
What kind of properties did they find?
Well, for the S275JR, they measured things like a yield strength around 307 MPa and an ultimate strength around 431 MPa. Standard stuff.
Oh, okay.
But for the S700MC, the yield strength was much higher, up around 772 MPa, and the ultimate strength was about 813 MPa.
Whoa, yeah, big difference in strength between those two grades.
Definitely.
And they use these steels to create specimens with different hole patterns, like the ones you see in real connections.
Yes, exactly. They tested 4 different configurations, which they show nicely in their papers, Table 1. There was Type A, just a single hole right in the center.
Simple case.
Type B, a single hole but off to the side, so it's eccentric. Type C had 2 holes side by side across the width. and type D had 2 holes, but in a staggered pattern along the length.
Covering common layouts.
Right. And the specimens had varying thicknesses and widths, appropriate for the steel grade, and drilled holes of different diameters, 18 millimeters for the S275, 12 millimeters for the S700MC specimens.
And they subjected these different specimens to different conditions, not just pulling them.
Correct. They had 3 main types of tests. First, they did just monotonic tensile tests, pulling some specimens straight to failure without any pre-existing cracks, just the baseline.
Okay.
Second, they performed pull tests on specimens that they had deliberately pre-cracked. These were labeled with a C in their results tables.
Pre-cracked. And the third type included the temperature variable.
Exactly. Those are the CT tests. They tested specimens that were pre-cracked and cooled. For these, they actually put the specimens in a freezer to cool them down to manacle 40 degrees Celsius first.
Minus 40 C. That's cold.
It is. Then they took them out and pulled them to failure at room temperature, but they made sure to record the actual temperature right near the crack tip at the moment the specimen broke.
And what temperatures do they get at failure? Still cold.
Yeah, the ones they reported in detail fractured with the crack tip temperature around 0 degrees C or negative 10 degrees C. So significantly below room temperature, even though the test wasn't done in the freezer.
Right. Now, creating those tiny specific cracks sounds tricky. How did they manage that reliably? Not just scratching it, right?
No, much more sophisticated. This is where they got clever. They induced fatigue cracks.
Fatigue? Like from bending a paperclip back and forth?
Sort of, yeah. They repeatedly pulled on the specimen with smaller loads, cycling the load thousands and thousands of times, typically between 10,000 and 100,000 cycles. This process initiates and slowly grows small cracks naturally from the edge of the hole, just like might happen in a real structure over time.
Okay, that makes sense for creating realistic cracks. But how did they stop the cracking process when the crack was still tiny? Finding a crack under a millimeter during a fatigue test sounds, well, nearly impossible.
This is the really ingenious part. They highlight the broken wire electronic sensor method. They show it in their figure 3.
Broken wire sensor.
Yeah. They glued a very, very thin copper wire about the thickness of a human hair, 0.1 millimeters right next to the edge of the hole, exactly where they expected cracks to start growing from.
Okay.
They hooked this tiny wire up to an electrical circuit. As soon as a tiny fatigue crack grew just enough to reach the wire,
Snap.
it breaks the wire, which breaks the electrical circuit. And that electrical signal was immediately used to tell the testing machine to stop the cyclic loading.
That is brilliant. So it automatically stops the test the instant a crack of a certain small size forms.
Exactly. It allowed them to reliably create specimens with these relatively small, controlled cracks, generally less than a millimeter, often in the 0.5 to 1.2 millimeter range, which is key because they wanted to study the effect of small defects, the 0.9 factor is supposed to cover.
That's really neat. Okay, so they had these carefully prepared specimens, different hole patterns, 2 steel grades, some with these controlled small cracks, some even tested after cooling. What did they measure during the final pull-to-failure tests?
The standard things you'd expect in a tensile test.
Mm-hmm.
The load being applied by the machine, how much the whole specimen stretched, usually measured by the machine's movement.
Mm-hmm.
And importantly, using a special sensor called an LVDT across the holes, they measured how much the steel stretched specifically in that critical net section area.
Ah, to see the local deformation.
Precisely. And of course, for the cooled tests, they tracked the temperature right near the crack.
All right, methods and measurements sorted. Let's get to the heart of it. The results. What did they actually find when they pulled these specimens until they broke?
Well, their main results are summarized in Table 4 of the paper. It lists the ultimate load reached in each experiment. New experiment.
The experimental failure load.
Yes. And they compared that directly to the ultimate load predicted by the Eurocode design rule, new calculated without the partial safety factor, just using the 0.9 factor.
Okay, and they confirmed they got those different kinds of small cracks they intended using that clever sensor.
They did. They documented the types of cracks they got. Some were corner cracks starting at the edge of the hole in the surface, some were semi-elliptical surface cracks, and a few grew all the way through the thickness.
Oh, mostly small.
Yes, the vast majority were quite small, typically under 2 millimeters in characteristic dimension, mostly between 0.5 and 1.0 millimeter. Average lengths were around 0.85 millimeters for corner cracks and 1.64 millimeters for the through thickness ones. Just the kind of small defects the 0.9 factor is meant to provide safety against.
Okay, so the big question then. What was the actual effect of having those small cracks present? Did it significantly knock down the ultimate strength compared to the uncracked specimens?
This was a key finding. Looking at their load elongation curves, like in Figure 4a, and comparing the results in the table, they found that the presence of these relatively small cracks marginally affected the failure load and also the deformation capacity, how much it stretched before breaking.
Only marginally.
That's what they reported. And this held true for both the standard S275JR steel and the high-strength S700MC.
Interesting.
They do add a note of caution, saying the sample size for each specific condition, like S700MC with a center hole and a crack, was limited, maybe only 1 or 2 tests. So while the trends seem clear across the board, strong statistical conclusions just about the crack effect alone are a bit limited by that small sample size per condition.
Okay, understandable. Minimal impact from small cracks observed in these specific tests. What about the low temperature effect on the S700MC? That's where you might worry more about the steel becoming brittle.
Right. But here, too, the results were perhaps surprising. Despite testing specimens cooled down to -40 degrees C, which then fractured at temperatures near freezing, like 0 degrees C or -10 degrees C near the crack tip,
Yeah.
they found no evidence of a reduction in the ultimate resistance due to the lower temperature tested, compared to the equivalent room temperature tests.
Wow. So even down to freezing, the ultimate strength didn't seem to drop for the S700MC in these net section tests.
Based on their limited CT tests, yes, that was the finding.
Okay. Was there any significant difference based purely on the steel grade? Did the much stronger S700MC perform fundamentally differently in terms of resistance compared to S275JR for the same geometry?
Well, this is another interesting point. For the specific hole configurations and the tension loading they applied, they reported no significant effect of the steel grade itself on the ultimate resistance related to the net section failure mode.
Wait, how can that be? S700 is way stronger.
It is, per square millimeter, absolutely. But remember, failure here is governed by the net section reaching its ultimate strength combined with the geometry. It seems for these specific geometries, the way the stress concentrated and the failure developed meant that the overall load capacity at failure wasn't dramatically higher for the S700MC specimens compared to the S275JR specimens with the same hole pattern. The failure mode itself seemed to limit the benefit of the higher material strength in this specific scenario.
Huh. Okay, that's counterintuitive but important. Now, the most critical comparison, how did their actual experimental results stack up against that Eurocode design rule?
Yeah.
The new ARD formula with the 0.9 factor.
Right, the bottom line check, and this is a key takeaway from the paper. They plot this in Figure 4b using what's called a unity check. It's the ratio of the experimental ultimate load, nu, xb,
What they actually measured.
divided by the load predicted by the Eurocode rule, nu, calculated without the partial safety factor but with the 0.9 factor included.
Okay, so nu xb divided by nu. If the rule is perfect, the ratio should be 1.
Ideally, or slightly above 1 for safety. And the headline result is, every single test they performed resulted in a ratio significantly above unity. Nu, expanding niggle, was greater than 1 in every single case.
Wait, run that by me again. You're saying every single test specimen, regardless of steel type, hole pattern, even the ones with cracks, even the ones tested cold, they all held more load than the Eurocode formula predicted they would.
That's exactly what their results show. For these specific geometries, materials, and conditions, the Eurocode design rule, including that 0.9 factor, consistently predicted an ultimate load that was lower than what the specimens actually withstood in the laboratory.
Precisely. It provides a safe, conservative prediction margin, at least for this range of parameters.
That's definitely reassuring to hear. Okay, what about the way the specimens failed? You mentioned capacity design earlier, wanting ductile failure. Did these specimens, especially the ones with cracks, snap suddenly, or did they stretch? Good question. They examined the broken pieces afterwards, and you can see photos in their Figure 5. The failure mechanism was overwhelmingly ductile.
Even with the cracks.
Even with the cracks. They noted that right near the crack tip, the high stress concentration, the triaxiality, might inhibit stretching locally. But the overall failure region showed significant necking, that visible thinning of the steel as it stretches before it finally tears. That necking is the classic sign of ductile behavior.
So despite the presence of cracks, the failure mode remained predominantly ductile. Good news.
Very good news from a structural safety perspective.
Now, how did that failure assessment diagram, the FAD tool, line up with all this? You mentioned they only applied it to some specific cases.
Yes. Due to the complexity of calculating the necessary inputs for all geometries, they focused the FAD analysis on the S700MC Type A specimens, the ones with a single center hole that were pre-cracked.
Okay, what did the FAD show for those?
Well, the FAD plots two ratios, KR, related to brittle fracture risk, and LR related to plastic collapse risk.
Yeah.
When they plotted the points for their experiments on the FAD, shown in their figure 6, all the assessment points landed squarely within the plastic collapse region of the diagram.
Plastic collapse, meaning ductile failure.
Exactly. It means the FAD predicted that failure would be governed by the material yielding and stretching excessively rather than by a sudden brittle fracture initiating from the crack. This perfectly matched their experimental observation that the failure was indeed ductile.
So the FAD analysis confirmed the visual evidence. Did it also predict the failure load accurately?
It predicted the mode correctly. And interestingly, like the Eurocode rule, the FAD predictions for the load were also conservative.
Conservative how?
The assessment points on the FAD plot fell outside the official failure line. This means the FAD predicted a failure load that was lower than what was actually observed in the experiments.
By how much?
On average, the FAD predicted failure load was about 0.86 times the experimental failure load, so about 14% lower. It showed the FAD approach was also safe, providing a conservative estimate for these cases.
So the FAD seems capable of predicting the behavior here, confirming the ductile failure mode and giving a safe load estimate.
It certainly appears so, based on this study. The FAD approach looks promising for analyzing these notched specimens with small cracks, even in high-strength steel. The main limitation, as they pointed out, is having the right solutions available to calculate the KR and LR parameters for different geometries and crack types.
Which might need fancy computer modeling for complex cases.
Potentially, yes. Numerical methods like finite element analysis could help generate those solutions when standard ones aren't available.
Okay, let's try and wrap this up. Let's put it all together for the listener. What are the key takeaways from this deep dive into the study by Leonetti and colleagues?
Well, I think the main thing is that this research provides really valuable experimental backing. It offers further evidence that the current Eurocode design rule for steel tension members with holes,
Including that specific 0.9 factor.
yes, including the 0.9 factor, gives a safe and reliable prediction margin, at least for the specific conditions they tested.
And those conditions included different common hole patterns, 2 different steel grades, standard and high strength, and importantly, even the presence of small cracks and testing at relatively low temperatures down to near freezing at the point of failure.
Exactly. In all those cases, the rule predicted a lower failure load than what was actually achieved.
And the tests also confirmed that failure was predominantly ductile in these scenarios, which is the preferred mode.
Correct. And that observation was consistent with the predictions from the failure assessment diagram analysis they performed.
So it sounds like this kind of experimental verification is crucial. It's not just about equations, it's about testing them against reality.
Absolutely. It's vital for validating and refining the engineering codes that ensure the safety of our built environment. It tests the assumptions and the safety factors built into the rules against how the actual steel behaves under potentially challenging conditions.
Essential work, then. Okay, so we've taken a deep dive into this fascinating study, seeing how experiments confirm the safety margin in a key Eurocode design rule for steel with holes under tension.
Even with small cracks and lower temperatures involved.
And how tools like the FAD support these findings by pointing towards ductile failure, which is what designers aim for.
Yeah, it reinforces the robust safety factors that are already built into our structural codes for these fairly common design scenarios.
Okay. But here's a final thought to leave you with, sort of building on what we've discussed. The study confirmed the design rule was safe and failure was ductile for the conditions tested.
Yes, that's always the important qualifier in research.
Right. They looked at specific geometries, relatively small cracks, temperatures down to near freezing at the moment of fracture. But what if you push the limits further? What if the temperature is much, much colder, Arctic conditions perhaps? What if the cracks are significantly larger or the geometry is more complex and induces even higher stress concentrations?
What if conditions do conspire to push the material towards brittle fracture, that sudden, potentially catastrophic failure mode, with little warning?
Exactly. How can engineers use research like this study and sophisticated tools like the FAD, which, after all, is explicitly designed to help understand that boundary between ductile and brittle failure? How can they use these to ensure safety in all potential failure modes?
Especially as we continue to use newer, stronger steels in perhaps more demanding applications in harsher environments than ever before.
That feels like the cutting edge, doesn't it? It's a question that surely continues to drive research and development, ensuring the incredible structures we rely on every day remain safe, not just under typical conditions, but under the toughest ones, too. Something to think about.